Acceleration. The velocity of an object in general changes during its course of motion. How to describe this change? Should it be described as a rate of change of velocity with distance or with time? This was a problem even in Galileo's time. It was first thought that this change could be described by the rate of change of velocity with distance. But though his studies of motion of freely falling objects and motion of objects on an inclined plane, Galileo concluded that the rate of change of velocity with time is constant of motion for all objects in free fall. On the other hand, the change in velocity with distance is not constant. It decreases with the increasing distance of fall. This led to the concept of acceleration and the rate of change of velocity with time. The average acceleration a over a time interval is defined as the change of velocity divided by the time interval. A equals v2 minus v1 divided by t2 minus t1, which equals delta v divided by delta t, where v2 and v1 are the instantaneous velocities or simply velocities at time t2 and t1. It is the average change in velocity per unit time. The SI unit of acceleration is meter per second square. On a plot of velocity versus time, the average acceleration is the slope of a straight line connecting the points corresponding to v2, t2 and v1, t1. The average acceleration for velocity time graph shown in figure 3.7 for different time intervals 0 seconds to 10 seconds, 10 seconds to 18 seconds and 18 seconds to 20 seconds are from 0 seconds to 10 seconds. Average acceleration A equals 24 minus 0 meter per second divided by 10 minus 0 second, which equals 2.4 meter per second square. From 10 seconds to 18 seconds, average acceleration equals 24 minus 24 meter per second divided by 18 minus 10 second, which equals 0 meter per second square. From 18 seconds to 20 seconds, average acceleration equals 0 minus 24 meter per second divided by 20 minus 18 second, which equals minus 12 meter per second square. Figure 3.8, acceleration as a function of time for motion represented in figure 3.3. Instantaneous acceleration is defined in the same way as the instantaneous velocity. Acceleration equals limit delta v by delta t as delta t tends to 0, which equals dv by dt. The acceleration at an instant is a slope of the tangent to the vt curve at that instant. For the vt curve shown in figure 3.7, we can obtain acceleration at every instant of time. The resulting at curve is shown in figure 3.8. We see that the acceleration is non-uniform over the period 0 seconds to 10 seconds. It is 0 between 10 seconds and 18 seconds and is constant with value minus 12 meter per second square between 18 seconds and 20 seconds. When the acceleration is uniform, obviously it equals the average acceleration over that period. Since velocity is a quantity having both magnitude and direction, a change in velocity may involve either or both of these factors. Acceleration therefore may result from a change in speed, that is magnitude, a change in direction to change in both. Like velocity, acceleration can also be positive, negative or zero. Position time graphs for motion with positive, negative and zero acceleration are shown in figures 3.9 A, B and C respectively. Note that the graph curves upward for positive acceleration, downward for negative acceleration, and it is straight line for zero acceleration. As an exercise, identify in figure 3.3 the regions of the curve that corresponding to these three cases. Although acceleration can vary with time, our study in this chapter will be restricted to the motion with constant acceleration. In this case, the average acceleration equals the constant value of acceleration during the interval. If the velocity of an object is v0 at t equals 0 and v at time t, we have average acceleration equals v minus v0 divided by t minus 0 or v equals v0 plus at. Figure 3.9, position time graph for motion with A. Positive acceleration, B. Negative acceleration and C. Zero acceleration. Let us see how velocity time graph looks like for some simple cases. Figure 3.10 shows velocity time graph for motion with constant acceleration for the following cases. A. An object is moving in a positive direction with a positive acceleration. For example, the motion of car in figure 3.3 between t equals 0 seconds and t equals 10 seconds. B. An object is moving in positive direction with a negative acceleration. For example, motion of a car in figure 3.3 between t equals 18 seconds and 20 seconds. C. An object is moving in negative direction with a negative acceleration. For example, the motion of a car moving from O in figure 3.1 in negative x direction with increasing speed. D. An object is moving in positive direction till time t1 and then turns back with the same negative acceleration. For example, the motion of car from point O to point Q in figure 3.1 till time t1 with decreasing speed and turning back and moving with the same negative acceleration. An interesting feature of a velocity time graph for any moving object is that the area under the curve represents the displacement over the given time interval. Figure 3.10 Velocity time graph for motions with constant acceleration. A. Motion in positive direction with positive acceleration. B. Motion in positive direction with negative acceleration. C. Motion in negative direction with negative acceleration. D. Motion of an object with negative acceleration that changes direction at time t1. Between time 0 to t1, its move in positive x direction, and between t1 and t2, it moves in the opposite direction. Figure 3.11 Area under Vt curve equals displacement of the object over a given time interval. The general proof of this statement requires use of calculus. We can, however, see that it is true for the simple case of an object moving with constant velocity u. Its velocity time graph is as shown in figure 3.11. The Vt curve is a straight line parallel to the time axis, and the area under it between t equals 0 and t equals capital T is the area of the rectangle of height u and base t. Therefore, area equals u into t, which equals ut, which is the displacement in this time interval. How come in this case an area is equal to the distance? Think. Note that dimensions of quantities on two coordinate axes and you will arrive at the answer. Note that the xt, vt and at graphs shown in several figures in this chapter have sharp kinks at some points, implying that the functions are not differentiable at these points. In any realistic situation, the functions will be differentiable at all points and the graphs will be smooth. What this means physically is that acceleration and velocity cannot change values abruptly at an instant. Changes are always continuous.